Section 7-4 is on graphical solution of differential equations using slope fields. The objective of this section is given a slope field for a differential equation, graph an approximate particular solution. So if you recall in the last two sections, we've been working with an algebraic solution using the separation of variables technique to come up with the algebraic solution to a differential equation. And now we're going to look at a graphical way to come up with that solution. All right, so let's start out with a definition here of what a slope field is. It's a graph of the slopes of a general function by a differential equation, given by a differential equation. So it's a graph of slopes. So as the name indicates, it's a slope field. So it's a field of slopes or a graph of slopes of a general function. And that's the key there is it's a function that you end up with, okay, given by a differential equation. So we're going to be looking at a graph that has a bunch of little slope marks indicated. And the solution that we're looking at has got to be a function. Okay, so when we go to do some sketching in a minute, you'll see that we have to end up with a function. All right, let's take a look at an example here to start off with. And this example, we're going to try to sketch the slope field of dy dx equals y. So I've got a window here set up from just 0 to 2 in both my x and y direction. And the larger your window, or I should say the more grid points you have in there, the more work you've got to go through. So that's why we've just got a couple here indicated. And basically what I want to do is I want to come up with points that I'm going to try to sketch the slope at each one of those points. So we're going to use the grid points that we have here, 0, 1, and 2 in both the x and y direction. And you can see that'll give us a total of 9 points here to graph, 9 slopes. So let's start out with on the bottom left, I guess. Let's start out at 0, 0. Oops, 0, 0. And what I want to do is find out what the slope is at 0, 0. So the slope at 0, 0, if I take my differential equation is dy dx equals something. And dy dx is a derivative, but derivative tells me slope. So this equation tells me the slope. All I got to do is plug in an x and a y value, and it tells me the slope at that point. So we have the point x is 0, y is 0. Now our differential equation is just dy dx equals y. There is no x. So just replace the y with the 0. So we end up with dy dx is equal to 0. So at the point 0, 0 on our graph, at this point right here, we have a slope of 0. So I'm going to just use this ruler to help me get a straight line here, but you don't necessarily have to have a ruler, of course, to do this. But we're just going to sketch in then a slope of 0 right at that point. So I'm going to draw in a horizontal line there that has a slope of 0. And that horizontal line represents the slope of that solution to this differential equation at 0, 0. All right, let's move on to the next point here. Let's find, let's go over, actually along the x-axis, let's go to 1, 0. If we go to 1, 0, dy dx again is equal to y, and the y value at 1, 0 is 0 again. So at the point 1, 0, right here, we're going to sketch another slope of 0. So we'll sketch that in there, something like that. And there's our slope at that point. And continue on. Let's move to 2, 0. And we'll get dy dx is equal to, again, it's equal to the y value, and the y value there is 0. So again, I'll just mark my point here, and we'll slide this ruler up. Straight edge is sometimes helpful there for making sure that's a nice slope field that you end up with. So there's the first 3 points. We have a total of 9, like I said. So let's continue on. The next value here to move to, I guess we'll move up. So we'll be at 0, 1. So at 0, 1, dy dx again is equal to the y value. And the y value at 0, 1 is 1. So now what I want to do is I want to change the slope there at x equals 0, y equals 1. I want to draw a line that has a slope of 1. So I'm going to use my straight edge again to help me do that. And basically, if I just use the fact that slope of 1 means you have a rise of 1 or a run of 1, I'll just mark that point right there that it heads towards. So this ruler now is marking a slope of approximately 1. It might not be exactly, but it's close enough for what we want to do. And we'll just simply draw our slope of 1. There we go. All right, let's move on to the next point there at x equals 1, y equals 1. So again, dy dx is equal to just the y value. We get 1. So again, if we come back to our graph here and plot a slope of 1, we end up with a graph that looks, or a point that looks something like that. I should mark that point there. And finally, if we finish out this line there at 2, 1, dy dx is equal to 1 again. You'll notice that we keep plotting the same slope there as we move across this line, and that's because the slope is not dependent on the x value, it's just dependent on the y value. It's just equal to y. So there is our slope at that point. All right, and let's finish up. I'm not going to worry about calculating, I guess, all of these across here. Let's move to 0, 2. dy dx is equal to 2. It's just the y value. So we'll sketch a slope of 2. And again, I'm going to use my ruler to help me do that. If I just put my ruler, say, at the origin and then angle it so it heads up towards the point at 1, 2, that's got a slope of 2 now. So we can just graph our slope of 2. And as you can see here, that's the slope at 0, 2. And the slope here at 1, 2 is going to be the same, so I'm just going to go ahead and mark that. And the slope at 2, 2 is going to be the same, so we'll mark that. And that right there is our slope field. So there's our first slope field there. You construct it by just simply plugging in points into your differential equation, and that tells you the slope at that particular point, and then plot a line with that slope. All right, let's take a look at another example. You can see that there's a little bit more to this differential equation here, or at least there's more to the slope field of it. It's obviously got a lot more slopes indicated. That would indicate, quite a bit more calculations that you have to do to get each of these. But let's take a look at example 1. It says the figure there shows the slope field for the differential equation dy dx is equal to this. Dy dx is equal to a negative 0.36 times x divided by y. There's our differential equation. And for this differential equation, for part A, they say to use that equation to find the slope at the points 5, 2, and negative 8, 9. Well, let's start out with the point at 5, 2. So at 5, 2, dy dx would equal, now notice this equation here has both an x and a y value in it. So it's going to be a negative 0.36 times the x value, which was 5, divided by just the y value, which is 2. And let's go ahead and punch that into our calculator and see what value we get. If we plug in a negative 0.36, oops, let me bring the calculator up so you can see me punch that in. A negative 0.36 times 5 divided by 2, we get a negative 0.9. Okay, so if we take our ruler again, let me bring up a ruler here so we have something to kind of measure with. If we look at the point at 5, 2, and let's first mark where that point is at. 1, 2, 3, 4, 5, and then up 2. That's going to be this point right here. And I can take my ruler then and kind of model that slope that I see there. According to our calculation, we should end up with a slope of about, well, it's about a negative 1. It's actually a negative 0.9 that we actually end up with, but I'm not sure if I can quite get to exactly the same slope, but we're pretty close right there. And you can look at that slope then and kind of try to determine whether or not it has a slope that you're expecting it to have. And if it has a slope of -1, oops, then I would expect that it, can't quite move it off that point there. I would expect that it kind of goes through the x-axis about 2 units below and over two units to the right, and that's kind of what we're seeing there. It's got a slope close to a -1. That looks like that's about the right value. Okay. Let's take a look at the other point they give us. The other point they give us is at -8, 9. So at -8, 9 dy dx is equal to a -0.36. Again, there's an x and a y value to plug in this one, so the x value is a -8 divided by y, which is 9. And let's go ahead and punch that into our calculator again and see what we end up with. So if we take a -0.36 times a -8 divided by 9, we get 0.32, which 0.32 is going to be close to a third. I guess is how we're going to approximate this. So 0.32 is this value. And let's find the point -8, 9. Go back 8 and then up 9. So that's going to be this point right here. And so again, let's change the slope of our ruler here to be about 1/3. Needs to go down a little bit there. Yeah, that's pretty close. We can adjust it just slightly there. So slope close to 1/3, I would expect to see that over a run of 3 units that it goes up 1 unit. And actually it looks pretty close to that when I look at the points that it's going through there. It's going, of course, through the point -8, 9, but then if I move over 3 units to the right, it looks like it goes through that point that's 1 unit above. So that looks pretty close to 1/3, which is what we're expecting, 0.32. So those look like the right values. All right. Let me just slide this over out of our way. All right, let's take a look at part B. It says for part B, start at the point 0,6 and draw a graph that represents the particular solution of the differential equation that contains the point, and then go back both to the left and to the right. And what geometric figure does the graph seem to be? Okay. So we're going to start at the point 0,6, they say. So I'm going to go ahead and mark that point as our starting point. So that's this point right here, 0,6. And when we go to sketch this thing, it says to sketch it both the left and the right. So as I go to the right, that's the direction I'm going to start with here. What I want to look at is I want to look at what slope I'm currently have, which if you look at the slope at this point, it has a horizontal tangent line there. And then as I head to the right, I can see since it's horizontal, I'm going to be heading towards somewhere between this slope here at 1,6 and this slope here at 1,5. It's not going to stay horizontal the whole time because I can see at 1,6 there, for example, it's slightly decreasing. And at 1,5 it's even more. So as I head to the right, I'm not going to necessarily hit either one of those 2 points, but rather as I head in that direction, I want to make sure that my slope as I approach x equals 1 has somewhere in between these 2 slopes here. All right. Sometimes you might be heading down, sometimes you might be heading up. In this case, based on the slopes that I see here, I'm heading down based on the slope I see at 1. So I know those are the 2 I got to consider. So when I go to graph this thing then, as I sketch this off to the right, it's going to slowly start to decrease here. And then as I get to 1, I'm going to then look at what's happening as I get closer to 2. So as I approach 2, I'm looking at, again, these 2 slopes here, and I want to sketch a line that goes through them. That's kind of the average of those 2 as it comes through those. So as I go to the right, it's going to look something like this. Again, I'm just trying to make sure it has a slope somewhere between those ones that I see there in my slope field. I'm probably dropping a little bit faster than I should be there, but that's all right. And then as I head to the right, again, I'm going to be looking at this slope here and this slope here at x equals 3. And I want to make sure my slope as it comes through there has about the same slope there. All right, and I continue doing this. I can see that I'm going to stay in between these 2 now. The slope is getting definitely a little bit steeper now. Okay, and I'm going to just continue heading towards the right here as I do this. And as I do it, I'm watching what slopes that I'm going through here to make sure my curve has the same slopes that I see on my slope field. So it's looking like this, and now all of a sudden it's going to really start to drop. and it drops something about like this, it looks like. Okay, so that's to the right. Now I've stopped there, and the reason that I've stopped there, I could actually try to continue making this thing come around. But if I do that, notice that at this point at 10, notice that along the x-axis there, I should say between 9 and 10, that the slopes actually become vertical. Along the x-axis, they're vertical. So actually the graph would start to come back around in this direction. However, we know that this has got to be a function. And so because of the fact that this has got to be a function, this is not going to pass the vertical line test, so I'm going to get rid of that little piece there because that's not part of my graph, not part of my solution. However, from my starting point at 0, 6, I can go to the left. And again, I'm going to do the same thing as I go to the left. I'm going to pay attention to what these values are that are to the left of x equals 0. That's at x equals -1. Now, you'll notice that if you look to the left and the right of the y-axis, there's some symmetry here. So that'll help you in sketching this as well, that actually what I graphed over on the right side is going to be a mirror image, a reflection across the y-axis here. But I'm going to sketch this by looking at the slopes here. I can see that at x equals -1, the slopes become slightly negative. So I'm starting out with a slope of 0, and I have to end up with a slope that's slightly negative. Not much, but it does drop a little bit. And then as I head to x equals -2, again, I'm going to focus on these two slopes that I see here and try to make sure that my graph mimics those slopes, or the average, if you will, of those two slopes, and so forth. And we're going to continue going through these points here and trying to watch what the slope is that my graph currently has and what slope it needs to end up with as I get to that x value. So it's going to look something like this, and like this, and it's going to go something like this. And again, I'm trying to look at what's happening over on the right side to help me out here, but also look at what slopes I'm going through here. Here's where it really starts to drop here at the end. You can again see that I'm trying to stay parallel to the slopes that I've got in my slope field. So it looks something like this. It's a little bit skewed here, I guess, with the with what I ended up with on the right side, but we're pretty close. Okay, not quite exactly the same, but we're close. And that's all we're looking for here. This is just you know, graphing it by hand and just kind of eyeballing it and trying to come up with the best approximation that you can for that solution. All right, so there would be our solution for that particular equation, or for that particular equation with the starting point or the initial condition of 0, 6. It asks, what geometric figure does this graph seem to be? Well, it looks like a semi-ellipse, a half of an ellipse. All right, look at part C now. It says start at the point 5, 2 from part A and draw another particular solution of the differential equation. How is this solution related to that in part B? Well, since we're going through the same slope field, and I can see that it contains basically the same general concept here, I'm going to expect to see the same shape, but it's not going to be the same size. Okay? It's not going to be quite as big of a semi-ellipse, but let's see what happens. So 5, 2 is this point right here that they gave us earlier to consider. And again, we're going to do the same thing, go from the towards the right as well as to the left as we go to sketch this thing. All right, so as I go to the right, again, you can see that I've got a pretty steep slope that we're starting off with. So I'm going to consider what slope I'm starting with, and as I head to the right, I got to think about, you know, what this slope is here and this slope is here, so that I make sure that I'm kind of going through those slopes, or at least being parallel to those slopes. So as I head to that in that direction, I can see this is a pretty steep slope here. We're going to hit the x-axis pretty quick as I go to the right, actually. All right, just past 6 it looks like. And now as I go back to the left, again, we're going to look at what's happening to the left of this point. I am going to be increasing as I go to the left. So I'm looking at those 2 points to kind of give an idea of what slopes I should have. And again, you're just trying to eyeball this as far as, you know, what looks like about the right slope between those two. All right, so let's see if we can sketch this. So it's becoming shallower as I sketch this between these points. And again, it's okay if your sketch is a little bit different than mine. I'm sure I'm going to have a sketch that's a little bit different than the books, but we're pretty close. All right. And as I continue sketching this, now again, since there's symmetry, I can use the fact that I hit the x-axis around 6, just past 6, so I'm going to hit the x-axis just past -6. And so that's at 2, 4, 6, -6 is about right here. We'll mark that kind of point. And then we went through the point at 2, 5, so -5, 2 is going to be a point that I'm going to want to go through. So I can use that to kind of help me sketch this, but I'd say try to get some practice of actually looking at your slope field there and getting a graph that goes through the slopes that you see there. Okay? All right, so there would be approximately what our solution looks like. And there is no one answer that's right, okay? When we're sketching this approximate, it's kind of like counting squares when we first learned how to find an antiderivative by approximating it with counting squares. You know, there was no one right answer that we were looking for. We just wanted to be in the ballpark. That's what we're looking for here. You know, on the other hand, if you were to start, say, down here, and all of a sudden you drew the sketch, you know, going in this direction, well, that's perpendicular to all the slopes that I see here. All my slopes are running in this direction, and my graph is running in the opposite direction, okay? Or at least it's running perpendicular to it, I should say. So that's definitely wrong, okay? So like I said, there's not one answer that's right, but there are some answers that are clearly wrong if they go against what you see in the slope field there. All right, now for a little bit of check here, I guess, to see if in fact this is a semi-ellipse or an ellipse like we are expecting from our graph. Look at part D. It says solve the differential equation algebraically and find the particular solution that contains the point 0.6. Verify that the graph really is the figure indicated there in part B. All right, so let's start out with our differential equation here. This goes back to what you did actually in sections 6.2 or 7.2 and 7.3, the previous two sections, of coming up with an algebraic solution to this. So we have dy dx is equal to a -0.36x divided by y. All right, now the only method that we know to solve a differential equation algebraically is separation of variables. So that tells me I need to take the dx, and that has to slide over to the right. Whatever's in the denominator has to slide to the right. And anything that's got a y in it over here on the right side has to move to the other side, so this is going to have to move over to this side. Okay? So I'm just indicating which direction things have to move, but that kind of gives us an idea of how we separate our variables. So I'll have to multiply by y, so it'll give me y times dy over on the left side. I've got to multiply by dx, so that's a -0.36 x times dx on the right side. And once you've separated your variables, you are all set to integrate this thing. All right, so the antiderivative of y, think of that as a power function here. It's y to the first power. So it's going to be 1/2 y squared. And that's equal to, I'll leave the constant out front, -0.36. And it's going to be 1/2 x squared. And of course, we always have our plus c at the end. So let's first, I guess first let's plug in our initial condition here so we can find out what this value of c is, and then we can get it into a form perhaps that we'll recognize. So the point they gave us was that x is equal to 0 and y is equal to 6. So we'll end up with 1/2 times 6 squared is equal to a -0.36 times 1/2 of 0 squared, that's nice, plus c. In fact, since this is multiplied by 0, he's all gone. So the value of c turns out to be 1/2 times 36. So c is equal to 18. So we know our value of c, so we can plug that in. So we have 1/2 times y squared is equal to a -0.36 x squared. Oops. 0.36 times 1/2 x squared plus 18. All right, now I have a 1/2 over here with the y squared, so let's multiply through by 2. So we end up with y squared is equal to the -0.36 times the 1/2, that will cancel out to give us just the -0.36 x squared. And then doubling the 18 will give us 36. All right, so the next step of this is, I guess, to get it in a form that we're going to recognize this equation, I guess. And so I'm going to move everything over to the left side here and write it as, I'll put the x squared actually out front here. I'll write it as 0.36x squared plus y squared is equal to, actually I'll put the minus 36 here as well, is equal to 0. Now this is actually the equation of a conic. And if you recall with the equation of a conic, the fact that there's no xy term there, that this guy right here being smaller than the coefficient on the x squared term there, on the y squared term there, which has a coefficient of 1, tells me that this thing is going to end up being an ellipse. The fact that they're both the same sign, both positive and not equal to each other, tells me it's an ellipse. However, to get it in a form that you might recognize a little bit better, I'm going to actually go back and rewrite it. I'm going to write it this way: 0.36x squared plus the y squared is equal to, I'm going to put the 36 back on the other side just to show you another way we can write this. Now let's divide through by the 36, so we'll have 0.36x squared over 36 plus y squared over 36 is equal to 1. And if we simplify this, we'll have x squared divided by 100, I guess is what we'll end up with there. 0.36 over 36 is 1 over 100, plus y squared over 36 is equal to 1. And if we write this in its factored form here as, x over 10 squared plus y over 6 squared is equal to 1, that might help us recognize that's the equation of ellipse centered at the origin with an x radius of 10, that's this guy, and a y radius of 6, which tells me I should expect it to cross the x-axis at 10 and the y-axis at 6. Well, we already know that it crosses the y-axis at 6 because that's where we started if we go back to our original graph. We didn't quite get it crossing at 10 like we were should end up with. We were at 9.5 maybe or so, but we're close. We're in the ballpark. That's what we're looking for. That right there is graphical solutions to differential equations using slope fields.